Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So, what would actually happen to like a human body if it was exposed to the vacuum of space? Because like, there's a bunch of different things in movies, like people explode or they freeze or they like freeze explode, and like I think I remember hearing about like fluids boiling horribly, and like I don't know how long you actually lived through any of this or if any of this is even what happens, but like what would actually happen?
You know, Lyons, I'm a chemist, not an astrobiologist. But with my very limited background and very limited area of expertise, I will attempt to opine to this question. So, short answer is you would die pretty quickly. But it would not be the Mr. Torque explosions. That is not what would happen. So you run into two problems in quick succession. So do you know the three, I mean, it's technically four, but the three general states of matter?
Yeah. So you have solid, liquid, gas, and I think the secret fourth bonus state is plasma.
It is.
Okay.
But the solid, liquid, gas, they become a problem in that opposite order, right? So first, because you got all three in you, right? And the first thing that becomes a problem is the gas in you, and then the next thing that becomes a problem is the liquids. So we'll start with gases. And so, you know, as we always like to do, first we like to create the universe before we bake a pie. So do you know what entropy is?
It's like that. It's the smoothing out of energy like over a space, right? So like energy doesn't like to be like condensed into a small space. It likes to kind of dissipate, right?
Mm-hmm. Yeah, that's pretty good. Technically, entropy is the measure of disorder in a system. So,
oh yeah, I'm picturing every like movie that talks about atoms and it shows like electrons whizzing around.
Yeah. Because that's the thing is that the universe is sloppy. And that's the honestly, and this is a tangential side story, but at one point I was in the middle of an audit, a science audit at my work, right? And the auditor said, you know, it's kind of interesting. I've noticed it's really easy to put new processes in place, but that it's difficult to maintain them. And just without even thinking, I said, well, the universe inevitably moves towards entropy and chaos. So it makes sense that things slowly degrade over time because eventually all of the universe moves towards heat death. And then there was this pregnant pause in the group. And an airman who's like 22 just turned to me and said, "Are you okay, man?" and I was like, "Yeah. What? No, I'm not like upset about that. I've reconciled my feelings about this. It is true, though."
Part of me was kind of hoping that the I believe you called them a science auditor was just gonna like slow clap and then just like tear up the evaluation like you pass.
And but then slowly like expand like the gases in the universe. So entropy is a measure of the randomness or disorder in a system. And so the question is, why does the universe move towards entropy, right? And it's actually, because I was always told like, well, the universe moves towards entropy. And as a young scientist, I was like, yep, got it. Makes sense. But then later on, I was like, but why? And it's actually a math problem, not like a physics or chemistry problem, which is there is just more ways to have disorder in the universe than order, you know? So
yeah. I mean, if you're talking about like the state of something, everything that's not a solid meter cube of steel is disordered, right? Like there's only one way a solid meter cube of steel can be a solid meter cube of steel, and it is to be a solid meter cube of steel. Everything else would be disordered from that state.
Correct, right? Or a good example of it is if you take a deck of cards, there is only one way for it to be in order, but there's 52 factorial ways for it to not be in order. So if you just randomly
a big old number.
Yeah, exactly. So if you just randomly said like, okay, I'm going to pick a random assortment of or like a random order of the deck, it is way more likely that it's not going to be in order. But it is, interestingly, it is possible for it to randomly become ordered, right? You know, but over time, you move towards disorder. I say all of that to say that, the universe abhors a vacuum, right? So to your point, right, is that if you've got like a whole bunch of stuff in one place and no stuff in another, the universe says, nah, I don't like that. I like a little bit of stuff everywhere, right? And so
I like
now have a follow.
To be very evenly buttered.
Exactly, right? If I've got, and it makes sense. And also, there wouldn't be life if not for this, because if the universe didn't move towards entropy, right, then there would just be one giant ball of heat gas mass, like somewhere, because it all just kind of glommed together. And then, the universe would be a pretty boring place. So let me ask you this. Where do you have a lot of air in you?
I think you might mean my lungs.
I do mean your lungs.
And probably a close second after that would be all your other organs, because they're also hollow.
Yeah, and we'll get to that. But you do have a lot of air in your lungs. And if you're in space, where is there not a lot of air?
Space.
Yep. Everywhere else. So that's the first problem that you have to deal with, is that basically, and this is interesting because, you can hold your breath, right, and not breathe for a little bit. But when all of the oxygen is forced out of your lungs, it basically makes you pass out very quickly, because you're not just sitting, your lungs aren't able to just chip away at the oxygen that's in them. It's all gone. And you don't want to hold your breath, because that will rupture your lungs,
Right, because the pressure inside would be higher than the nothing pressure outside.
Right. Yeah. And it's the same thing when you're scuba diving, right? So if you are down at like 60 feet underwater, you take a deep breath from the regulator. The last thing you want to do is just shoot up and hold your breath, right? You're supposed to be breathing regularly, because then that equalizes the pressure in your lungs, right? So basically, the only thing you can do is let all of the air out of your lungs, which basically immediately makes you pass out, right? So that's the first thing that happens is the body is the main thing your body needs to stay alive, oxygen, is all taken away from you. So now the clock is ticking. The next thing that you have to start to deal with is liquids. And so let me ask you this. At what temperature does water boil?
In science units or freedom units?
Oh God, freedom units. No, I'm taking that. That's
in science units, water would boil at 100 Celsius.
Mm-hmm.
In freedom units, it's 212.
Yeah. Hey, good job. Yeah. So yes, that is true at one atmosphere.
Sea level, yeah.
At sea level, right? But if you were up in the mountains, it's less. Why?
Lower ambient pressure.
Exactly. So basically, water boils so there's a vapor pressure over the water, right? And as you heat up the water, it increases the vapor pressure. When the vapor pressure is equal to the ambient pressure, it boils. Does that make sense?
It does.
Okay. So when the outside pressure is 0, right, it doesn't take anything for stuff to boil, right? So basically all of
which is interesting, because I think most lay people, myself included, would think of boiling as like you have to add energy to the system. And it's like, right, you do, because in that environment, it is below the necessary energy to go gaseous, right? So you can add energy to the system, or you can take pressure out of the environment, and now the energy in the system is sufficient.
Yes. Yeah, exactly. Yeah, it's one of those things where PV equals nRT, which is the ideal gas law. And, if you...
I swear to God, you probably have a t-shirt with that or something.
It's one of those things that is just rattled off at you so many times that you're just like PV equals nRT. I say all that to say that, so basically, eventually, to your point, right, is that like in order to get something into a different state, it's a fraction, right? And so it's like, well, like I need to get this into this other state. Well, it's like, well, you can increase the temperature or decrease the pressure, either or. They're both, they're all good equations, Brent. So the thing is that then any liquids that have access to like the vacuum directly, because your body does have some degree of pressure in it, right? Like your body has internal pressure, right? But so that means your saliva, your tears, anything that is liquid on your person, God help if you were sweating, all of that boils immediately, right? So kind of a bummer. One of the astronauts.
I don't know why the tears one is just the worst. Just something about like the water in your eyes.
Eyes, yeah, yeah. Because like, I think it's because like you can conceptualize drinking boiling water, like it would burn you, but it's like, but the idea of putting boiling anything in your eyes is like. I just don't think that. Whereas like conceptually, like that should never. Why would you do that? So yeah, so that's no bueno, right? So then, and actually, the one of the astronauts, there was an astronaut or a cosmonaut at one point in time that. So no, I take that back. It was somebody working in a pressure chamber, right? And then something with their suit went wrong, and the suit lost pressure in like a zero pressure environment. And they said the last thing I remember feeling before I passed out was my saliva boiling.
Ah.
You know? And you got to figure, like, if you can even still form cogent thoughts, like, this is probably it, you know? Like,
yeah. Well,
as you're passing out, right?
I wouldn't be surprised if it's like part of the reason the last thing you remember is because that thought crossed your mind. And then your mind was like, time to stop thinking thoughts.
Yep. Shut it all down. The person in your brain goes to the big giant lever and just turns off all of the lights. It looks like the final season of like a sitcom. They kind of like look around the brain space and they're like, all right,
yeah,
you know,
the sad acoustic guitar version of the theme song.
So then the final thing is that so the liquids inside of your body start to go with problems, because part of the issue is that your blood, right? You think of your blood as like a liquid.
I do. I do think of my blood as a liquid all the time, ideally.
I have a friend of mine that worked in like a blood bank, basically, with the military, and he goes, blood, there is so much more blood in like a packet of blood than you think, mostly because it's like if you spill water, you don't think about it. But he's like, somebody spilled blood and it looked like an anime set. Like, you know,
we now live in the Kill Bill universe.
Yeah, where he's just like, if you spill, because it's a pint, right? It's like you spill a pint of water on the floor, you're like, oh, well, I'll clean it up. You spill a pint of blood on the floor, you're like, 15 people died, you know? So, and your blood is a liquid. However, what your blood does have a lot of, and is very important, is dissolved gases, right? Like oxygen, you know? And so the thing is that those oxygen bubbles are super duper tiny, right? Under a certain pressure, right? But if you suddenly drop the pressure, they get way bigger. And I learned a technical definition for something, which is an embolism, you know? So,
unfortunately, I know that word because of like family medical history,
and I know you do, and so I didn't want to like you know, like beat it to death. But normally, an embolism is like, oh well, something clots in your blood, and then you know it causes a blockage. But technically, the embolism is just the blockage. It's just that 99% of the time on Earth, it's going to be a clot in the blood, right?
Right. A solid, not a gigantic gas bubble.
Not a gigantic gas ball. So the thing that generally will eventually kill you is that the gases expand, and as they kind of all conglomerate together, they will form an embolism that will clog you somewhere and kill you. You know? So
that's the first thing, right? So like other things would have killed you, like the lack of oxygen and stuff, but like the thing that would immediately be recognized as the cause of death would be that.
To my understanding, yes, is that the thing that kills you would be the embolism, right? The lack of oxygen, because even when all the oxygen is pulled out of your body, that just causes you to pass out, and then for your cells to start to die and decay and all this sort of stuff. Like you start to suffer brain damage and all that sort of stuff. Also, too, you know, like depending on where you're at, if you were just jettisoned out into space, right? If you're in line of sight of a star, like you'd be horrifyingly radiation scarred, you know? But we were kind of, because that's the thing, is that like the sun just pelts you with all kinds of radiation. It's just the atmosphere does a great job of mitigating a lot of it, you know? So, I mean, like all of those are things that happen to you, but my understanding is that basically what you would be somewhat aware of is that all of the oxygen would be forced out of your lungs, as the last things you were being aware of is all of the liquids on your body boiling, and then your blood would form an embolism, and that would kill you. And then all of the other terrible stuff would happen. You know?
to your corpse.
Yes.
So I do have one clarifying question. Because you made me realize that a few very famous scenes from shows and movies I like are just complete bunk, which I knew, but now I know how they're bunk. Would your corpse eventually freeze in a way that like we on Earth would identify something being frozen? Because like if you take like a steak out of the freezer, it is frozen and it's got like little ice crystals on it and stuff, but like you are mostly meat, or there's a lot of meat that like makes up a person. So like if you exposed to the non-elements were thrown into the vacuum, like would you freeze in a way that we think of a like meat freezing?
Yeah, I believe that basically what would happen. So because that's the thing is that once you, and this is where it's interesting because like once you kind of start to move away from like after you've died, you are way more. You're starting to eke more into like biology physics area as opposed to biology, anatomy and physiology, right? Because it's like, well, you're dead now. So now to your point, we are more so talking about like, well, does warm meat freeze? And yeah, like you are a certain temperature of like inert materials now. And slowly over time, like, yeah, all of that would freeze. Your blood would freeze. Everything would kind of freeze as you started to inch towards, it's not 0 degrees Kelvin, but like a low Kelvin state. And your everything would become super brittle, So like if you were to bring somebody in, they would, like be brittle to work with. And again, like the being near a star question like throws an extra wrinkle onto it because that would burn your like radiation scar your skin and tissues, and I don't know like what like if you just left somebody in line with a star like that, if they would like what would happen then if the radiation would like kind of rip apart all the cells and membranes and stuff and kind of effectively disintegrate you and over what period of time. But I would think that the most complex situation would be you're in space, you're within view of a star, in which case then first you die. Then your body would freeze, and while your body was freezing, actually I take that back. I know what would happen is that like the side of your body that was facing away from the star would freeze. The side that was facing the star would burn, and then it would just slowly burn through until
right,
and then the amount of you that was frozen would be the coefficient of the thermal coefficient of your body of how well it translates heat from the warm side to the cold side.
Yeah. So like an apple pie from McDonald's, you would be simultaneously frozen and scalding hot.
Yes, yeah, it would be just like fish sticks made by your children, somehow burnt on the outside and frozen on the inside.
You know what? That reminds me of another question I wanted to ask you.
Oh God.